So today's video I'm going to be going through just a quick recap of all the mechanisms that I've got on these couple of pieces of paper stapled together. It's not going to be a separate video. So one, draw a reaction mechanism to show how chloromethane with NaOH, sodium hydroxide, forms methanol and NaOH and NaCl. This is the basics, the literal fundamentals of mechanisms. So in this case, OH minus with lone pairs of electrons attacks carbon, CCl bond breaks, and it's just being replaced, and Cl minus leaves with the lone pair of electrons, and this is nucleophilic substitution, obviously. So CCl bond breaks, electrons move from OH minus lone pairs to carbon to form a new bond. Electrons move to chlorine atom, and the overall charge of reaction stays the same. Then we move on to two initiation reactions where free radicals are produced. So we got Cl2 chlorine with UV light to form two chlorine free radicals. Now the sunlight provides enough energy to break the Cl-Cl bond, and the bond splits equally. Therefore, there's Cl free radical unpaired electron. A propagation reaction, the free radicals are used up. Cl dot plus CH4, CH3 dot plus HCl, and then CH3 dot plus Cl2, CH3Cl plus Cl dot. And then termination reaction where the free radicals are removed. Cl dot plus CH3 dot CH3Cl, two unpaired electrons form a covalent bond, and the free radical is a particle with an unpaired electron. Number 3, O2 with UV light form O dot plus O dot, two free radicals, single oxygen. Then O2 plus O dot to form O3, and this is how ozone is formed. I've never seen a question on this, so this could come up in future past papers. I would learn it. O2, two free radicals, and then O2 plus O dot to form O3. And then it says write two equations show how chlorine free radical catalyst catalyzes ozone molecules. This comes up quite a bit. Cl dot plus O3, Cl dot plus O2, Cl dot plus O3, 2O2 plus Cl dot, free radicals are the catalyst, and therefore you can see once you add them together and you cancel out both left side, right hand side, you get from 2O3 to 3O2. Then halogen alkanes can undergo nucleophilic substitution. Nucleophilic substitution reactions when a nucleophile can react with a polar molecule by kicking out its functional group and replacing it. So here, lone pairs of electrons, nucleophile, Br whatever it can be, OH minus, attacks the carbon, positive, and the CX bond should break. Didn't draw it out, but yeah, it should break. And then you've got this with the nucleophile replacing the X, and the X leaves with the minus and lone pairs of electrons. 3 types of nucleophiles that can react with halogen alkanes: OH minus, Cn minus, and NH3, and you do need to know each and every single one of them. So for this one, halogen alkanes react with hydroxides to form alcohols, hydroxide OH minus. This one, halogen alkanes react with cyanide to form nitriles, and then halogen alkanes can react with ammonia, with excess ethanolic ammonia to form amines, I think. Then we got halogen alkanes can react with hydroxides to form alcohols, the OH minus one. In order for nucleophilic substitution reaction to occur, you have to use warm aqueous sodium or potassium hydroxide. Warm aqueous sodium or potassium hydroxide. So you can see here the lone pair of electrons OH minus attacks carbon, CBr bond breaks, and the Br minus leaves with the lone pair of electrons negative charge. Delta positive carbon attracts the lone pair of electrons from the OH minus sign, the CBr bond breaks, and the bromine leaves taking both electrons, and the COH bond forms. Nitriles are formed by reacting halogenoalkanes with cyanide, or halogenoalkanes can react with cyanide to form nitriles. Yeah, same thing. Halogenoalkanes can react with cyanide to form nitriles. Nitriles have the C triple bond N group. So you can see here the C triple bond N with lone pair of electron negative charge attacks the carbon, CBr bond breaks, carbon's partially positive, bromine's partially negative. That makes a lot. That's pretty simple, like these last couple of mechanisms we've gone through. However, in this case, we need to use reflux and ethanol. So it needs to be in reflux conditions and dissolving ethanol as well. And then you can form your nitrile CN and then your Br minus the lone pair electrons. And remember, it's CCN. It's not C triple bond CN. This triple bond goes away. It's just bonded like normal CCN. But you do need reflux and ethanol for this case. So I could see that potentially being a 2 marker state, condition, and state, condition, and reagent used, and reflux and ethanol in this case. So do conditions for nitriles to be formed by reacting halogen alkanes with cyanide. We want to warm the halogen alkane, with ethanolic potassium cyanide under reflux. Now this one, halogen alkanes react with ammonia to form amines. This one's obviously a bit different because the 2 conditions necessary for halogen alkanes to react with ammonia to form amines. We want to warm a halogen alkane, like just the previous one we went through. We want to warm a halogen alkane with ethanolic potassium cyanide, reflux and ethanol. And that was for nitriles being formed by reacting halogen alkanes with cyanide. In this case, we want to form amines by reacting halogen alkanes with ammonia. We want to warm a halogen alkane with excess ethanolic ammonia.